Hello everyone, my name is Logan. Welcome back to the lecture hall. Today we're covering section 2.5 for our UCI Math 2A course, continuity. So let's start with a definition of continuity. A function is continuous at a if the limit as x approaches a of f of x is equal to f of a. So this definition has three things. Also, heads up, this lesson is a lot of definitions that you just have to kind of know and make notes of. So it's going to be me just a lot of reading off what's on the board, but I mean, it's going to be a little boring, but you just got to know it. So get your pencils ready. So what are the three things that this definition requires? First, it requires that f of a be defined. So f of a equals something, you know? Then it also requires that the limit as x approaches a of f of x must exist, right? So this has to be a real thing. It has to be real. And then the last thing is what the definition says, is the limit as x approaches a of f of x is equal to f of a. So that is how you know a function is continuous at a singular point. So definition 2. A function is continuous from the right-hand side at a if the limit as x approaches a plus of f of x is equal to f of a, right? And then it's the same thing for the definition from the left. A function is continuous from the left at a if limit as x approaches a minus of f of x is equal to f of a. And the limit exists if both are correct, if they both approach the same a, or, well, the same f of a. So, definition 4. A function is continuous on an interval if it is continuous at every point in the interval. So, for every single point on your interval from a to b, right, if this holds for every single one of them, if the limit as x approaches a of f of x is equal to f of a, for every point on your interval from c to d, then it is a continuous function on that interval. So for continuity, it's pretty simple. You know, as long as there's no gaps, breaks, or holes in the graph, then the function is considered to be continuous. So now we have a theorem. And we're obviously not going to prove it because we don't need to prove it, but the theorem states that if f and g are continuous at a and c is a constant, then the following are continuous. F of x plus g of x is continuous. F of x, or I should say f of a plus g of a is continuous. F of a minus g of a is continuous. C times f of a is continuous. F of a times g of a is continuous. And f of a divided by g of a is continuous if g of a does not equal to 0, because obviously if it equaled 0, then you'd have f of a over 0. You can't have anything over 0. So, another theorem. What did I say earlier? It's just a lot of theorems in this one. It's kind of annoying. Another theorem. Any polynomial is continuous from negative infinity to positive infinity. So that's like your x squareds, your x cubes, your 5x to the 4th plus 3x squared plus 2. You know, that's those functions. And then any rational function is continuous on its domain. So what's a rational function? Just in case we did go over it, but you know, doesn't matter if you forget it. Rational functions. It's two polynomial functions, one over the other. So p of x and q of x are both polynomial functions. Now on to the next theorem. The following functions are continuous on their domains. Polynomials, which we already saw, rationals, which we already saw, root functions, trig functions, inverse trig functions, exponential functions, and logarithmic functions are all continuous for along their domains. Alright, on to another theorem. Who would have guessed it? No, so the theorem, if f is continuous at b and the limit as x approaches a of g of x is equal to b, then the limit as x approaches a of f of g of x, composition function is equal to f of b. So this is the same. This double implies conditional or double conditional. This says the limit as x approaches a of f of g of x is equal to saying the limit as the function of the limit of x approaches a of g of x. So it's kind of weird to say out loud, but pretty much the limit as x approaches a of f of x is the same thing as taking the limit of g of x and then plugging that limit that you got, your b, into your f again, and then you get f of b. Alright, let's do an example of this theorem. Limit as x approaches a of arc sine of 1 minus square root of x over 1 minus x. That's the same thing as saying arc sine of the limit as x approaches. Oh, I said a. It should be 1. Whoops. As x approaches 1. Alright? And then 1 minus square root of x over 1 minus x. Right? Okay, that looks fucking scary. Yikes. That looks scary. So, let's do this lim as x approaches 1. Well, so we see 1 minus x and 1 minus root x. Well, what can you do? Well, you can break up the bottom. You can factor it out and have it be 1 plus square root x, 1 minus square root x. And then, hey, would you look at that? Would you look at that? Those cross out, so you just have arc sine lim as x approaches 1 of 1 over 1 plus root x, which is equal to lim is equal to, because you can just plug in 1, because 1 works for it. It's not, nothing's going to be over 0. You have 1 over 1 plus 1, which is equal to 2. So then arc 2, 1 half, geez, it's 1 over 2, yeah, it's equal to 1 over 2, 1 half. And then arc sine of 1 half, this, you just kind of have to know, you have to look at the unit circle, you just have to, that's just one of those things you got to know, is equal to pi over 6. So, that is how you use this theorem. Alright guys, there are only 2 more theorems to go and then we're done. The last 2 theorems. If G is continuous at A and F is continuous at G of A, then the composite function f of g of x is continuous at A. So, and then f of g of x is the same as f of g of x. You know, those are the same thing. Alright, now on to the last theorem. This one's actually incredibly important. This one is called the intermediate value theorem. So, suppose f of x is continuous on an interval from a to b. And then let n exist such that f of a is less than n, which is less than f of b. Then this means, then there exists that some c, some random c, is in a and b such that f of c equals n. So what does this even mean? Well, let's look at it on a graph. Alright, so you have your f of a, we've got a red pen, f of a here, your f of b, and you have some n right here. N, right? So, the function has to be continuous from here to here, right? So that means that an n is in between these two. That means there has to be a c where it equals n, f of c such that it equals n, because it's continuous, right? If you had a graph that was like this, then it wouldn't work, you know, like a step function or something. Then it makes sense that there isn't a number correlating to right here, right? But since it's a continuous function, that means that if there's an n in between f of a and f of b, that means there has to be a c in between a and b such that f of c equals n. So, I know this was a lot of theorems, but they're all really important. So now, let's transition into some practice questions. Alright, we're doing numbers 15 and 4. So we'll start at 4 over here. It's state the intervals that g is continuous on. So, well, let's find the intervals. So, when you see a hole, you know it's not continuous, right? So from here to here, not including the hole. It's not continuous here. It's continuous here to here, not including the hole. So then that's -1, -2, -3. 1, 2, 3, negative. Alright? So it's from here to here, but not including those. Alright, so it's from 0 to 2, and then there's an asymptote here at -2. So it can never equal -2, but it is continuous to -2. So from here to here, which would be from here to here, here to here, here to here, right? And then there's a point here, so from here to here, right? So from here to here. And then from 2 down all the way. So we'll say this point is at 2.5, right? So, where is g continuous? G is continuous from -3. It includes -3, that's where the bracket comes from. But does not include 2.5. So there's a parenthesis. Then it is continuous from 2.5 to infinity. Or wow, to 2, but it can't include either of those because the graph never equals those. Then from, oh, and those are negatives, and then from -2 to 0, it includes 0, it doesn't include -2, right? And then from 0 to 1 doesn't include either because there's holes right there. And then from 1 doesn't include all the way to 3 where it does include, right? So this is pretty easy. It's just to kind of get you to realize what continuity is and what it looks like because you see all the holes, and whenever you see a hole, you know it's not continuous. Alright, now on to problem 15. Prove that it is continuous. Well, this one's really quite easy because if you remember, it's one of our theorems that we had that says these functions are all continuous on their domains. So polynomials, root functions, rationals, all of those. Well, what is this? This is a polynomial function. And we know that polynomial functions have a domain from -infinity to +infinity, and they're continuous on that domain. Because this is essentially saying x to the 1, which is a polynomial, right? So this is continuous, and the addition of two functions is also, if they're both continuous, then it's continuous. So you have one continuous function, and then, what is this? Oh, you have a root function. Well, what is the domain of this root function? It can never be negative, but it can equal 0. So that would be from 4 to infinity. So that is this, right? So the domain of this is continuous on its domain by our theorem. So we have a second continuous function. And when you add two continuous functions, you get another continuous function. So f of x is continuous. Alright everyone, thanks for watching. My name was Logan. Have a great day.